Hey Physics 20s, welcome back. Today we're going to talk about gravitational potential energy and also mechanical energy, just sort of an idea of what mechanical energy is. But we are in Unit 4 and we are on page 124. So if you're not already there, get out your workbook and we will get started. Cool. So gravitational potential energy, our first little bit that we're going to look at here. This is stored energy. Anytime we have potential energy, it is stored energy. That means it doesn't really doing anything yet, but it's got the potential to do work on an object. And that brings us back. I mean, work is equal to a change in energy. So when we change that object's energy, it's got the ability to do work on something else. We're always coming back to that, aren't we? So something to consider, similar to what we talked about before, is how do we know that this green object up here, how do we know that that object has gravitational potential energy? And we said, well, if it's got energy, it has the ability to do work. So we can think about this. It is just resting. Like there might be a hand holding this object up here or something like that. It's resting. And then it might be resting above a block of wood with a nail sticking out of it. So the entire time that that object is being held there, nothing's going to happen. But does it have potential to do work on that nail? If the person were to let go of it, could it apply a force over a distance on that nail and drive it in? And if you're thinking absolutely, like you've probably done that before, then you're spot on. So it can. There we go. It can push that nail inward, so it can do work on the nail. Therefore, it has energy. Cool. All right. So what we're kind of looking at here, I don't know if we need to get into this one too much, but deriving the equation for this, we might as well. It'll take us a couple seconds. You could probably skip ahead if you really don't want to. But deriving the formula, so we talk about work is equal to a change in energy, right? So in this case, we're talking about work is equal to a change in gravitational potential energy. So EPGF, minus EPGI. Cool. But if it's starting on the ground, it can't really go anywhere else. We're going to say that it's got 0 gravitational potential energy. So our initial spot is going to be absolutely nothing. So starting on the ground, we've got nothing. So our work done is equal to our final gravitational potential energy. So we can expand on this a little bit. Let's see. Our work is equal to our force times our distance, which again is equal to our gravitational potential energy at that final height. But if it's moving up at a constant speed, we can think back to Unit 3, and a constant speed, what does that tell me about the forces? It tells me that those forces are balanced. So I've got force of gravity going downwards, I've got my applied force going upwards, and they are balanced. So really, we're working against our force of gravity here. So the work that we are doing lifting that box is working against the force of gravity times the distance, but we're not going to necessarily call that the distance, we're going to call that the height. So let's expand on that a little bit. We know that force of gravity is mass times gravity, and we know that we're going to call this distance, in this case, the height. Oh, look at that. The work done to lift an object up to a particular height is equal to its gravitational potential energy. And hey, there's our formula, mgh. You probably remember that from Science 10. Mass times gravitational field strength or acceleration due to gravity times the height. So there we have it, our formula. Notice it's also measured in joules. Perfect, measured in joules. See if you can get from that a joule, and see if you can figure out from previous lessons, we talked about how a joule is also a kilogram times meter squared over second squared. So see if you can plug that one in and see. Some things to note with this formula. Mass is a scalar, obviously. Gravitational field strength or acceleration due to gravity in newtons per kilogram or meters per second squared. It's the magnitude only, so we're not including any direction there at all with our gravitational field strength. And then height is the height of an object, also a scalar, or h, sorry, is the height of the object, also a scalar, so no directions there whatsoever. Cool. So determining heights, this can be a little bit tricky because you might be sitting on the second story of your house and you might want to call the floor the lowest place in the room. But is there things that are lower than the floor? Absolutely. Same with this. Like if I call my reference height A, so the reference height is just the height that we're going to say is 0. That's all there really is to it. So if I looked at A and I said that A is a height of 0, I'd look at part B and I'd say, oh, well, that's 12 meters above it. That's 12 meters higher. I might say that that's plus 12 meters. But then if I look at B, well, saying that height at A is 0, or sorry, at C, I should say, C, it's 15 meters below that. So we have less height. Again, not really a direction. It's just we have more height or we have less height above or below. So we can put that in. So that's if A is our reference height. What if we put C as my reference height, right? So if I said that C is my reference height, I'm saying C has a height equal to 0. Well, that means at part A, or point A, sorry, our height is equal to positive 15 meters. And at part B, we've essentially got our height, I keep saying point B, our height is, let's see, 27 meters higher than at point C. So realistically, the reference height can change depending on your perspective, right? And it's important to note that reference height. Typically, I like to put it at the lowest point. Okay, but let's check out an example here. Let's see how this all kind of fits together. We get a 350 gram object initially at a height of 64 centimeters. It then gains 800 mJ, oh, that's millijoules, of gravitational potential energy. Determine its final height. Okay, so let's just go through and let's work with some of these numbers. First one is a mass, and I realistically want that in kilograms, not grams, so 0.35 kilograms. The second one is our initial height, so I'm going to put that as HI, and centimeters, come on, centimeters, 0.64 meters is what we're really looking for. It gains this much gravitational potential energy, so that's my change in my gravitational potential energy. I'm going to say that that's equal to 800 millijoules, or 0.8 regular joules. So I divide that by 1,000 to get it into joules as opposed to millijoules. Now it is gaining 800 millijoules, so that means I'm going to put that change as a positive 0.8 joules. Cool. And then determine its final height, HF, that is our question mark. Awesome. So we figured out what's going on with this. One thing that we might want to think about is its final height going to be higher or lower than its initial height? And you're probably thinking to yourself, higher, absolutely. So let's go through and let's set this up a little bit here. I got my change in gravitational potential energy is equal to EPGF minus EPGI. So that's no problem. If I'm looking for my final height, I'm going to find that in my final gravitational potential energy. So there's a bunch of different ways that we could potentially look at this. We could do this in a bunch of smaller steps, or I could do this in one really big step, or a bigger step and a smaller step. I think what I'll do is I'll rearrange and I'll solve for my final gravitational potential energy, because I know that's what I'm going to have my height in. So it's going to be equal to my change in energy plus my initial gravitational potential energy. Cool, so all I did was take this one, move it to the other side. I was subtracting it, so I want to add it to both sides of the equation. So let's expand on this. I know what my change is, so I'm just going to leave that as is. And then my initial is mghi. Cool. I know the mass, I know gravity, I know height. I think we can plug in all the numbers here. I think we're good to go. So our change in was positive 0.8 joules plus the mass, 0.35 kilograms, times 9.81 newtons per kilogram, times the height. Okay, what was the height again here? 64 centimeters, or 0.64 meters. So put your video on pause, plug the numbers in, and see what you end up with. So I ended up with 2.99744 joules. And again, that is my final gravitational potential energy, EPGF, F for final. Cool. So Last thing that I really want to do is if I know my final gravitational potential energy, I know my mass, I know gravity, I can solve for height. So EPGF is equal to mg times hf. Cool. Okay, then hf, so I'm just going to divide both sides of the equation by m and g, is going to be EPG divided by mg, and I can go ahead and solve this now. So 2.9944 joules divided by the mass, 0.35 kilograms, and also divided by g, 9.81 newtons per kilogram, or you could again use meters per second squared there. So again, plug your numbers in. You can put it on pause if you need to. But please actually plug numbers in and make sure we're getting to the same place. So I ended up, when all is said and done, with, I think I'm allowed 2 sig digs. I better double check that. Back to the original question. Nope, 3 sig digs. So 0.873 meters, or if we really wanted to, we could put it back into terms of the question, 87.3 centimeters. Either of those work out just fine for our final height. Now, if it gained potential energy, does it make sense that it's higher than its original? Absolutely it does. Perfect. Okay, so there's our first one that we're looking at, still dealing with that change in. And again, there's multiple different ways that you could do this. You could try it out in one really big step if you wanted to, or you could try it out in a bunch of smaller steps. So you could calculate, I'll use a different color to highlight a bit here. You could calculate EPG, our initial EPG. Then you could go through and solve for your final gravitational potential energy. And then you could do our final step here. Or you could do this all at once. So you could expand this entire formula up top here and expand on every single little piece of it to solve for your gravitational, or sorry, for your final height. Cool. Okay. Last little bit to talk about here is our mechanical energy. Mechanical energy, EM, and if you haven't noticed this yet, E stands for energy, and then we're using little subscripts to talk about the type of energies. For example, EM for gravitational potential, EK for kinetic energy. I said EM, gravitational potential. That's not at all correct. Mechanical is EM. Kinetic is EK. Okay. So mechanical energy, just a umbrella term for realistically for all these different types of mechanical energy. So kinetic, gravitational, and spring. Spring is in brackets. We haven't really dealt with it here. So realistically, EK plus EPG for now. So that's really all there is to it. Just all of those different types of mechanical energy added up. So quick example here. We've got the gravitational potential energy at A is 0. What does that mean my reference height is? So if EPG is equal to mgh, and I've got 0 gravitational potential energy, that means this side of the equation also needs to be equal to 0. Well, I can't have 0 mass, can't have 0 gravity. That means that this has to be my reference height. This is a height of 0. Cool. So it says the gravitational potential energy at A is 0. So we've dealt with that one. And it moves at a constant speed. So if it's 11.2 kilometers per hour at the top, and it's a constant speed, it's going to be 11.2 kilometers per hour at the bottom. So the speed hasn't changed. Now, kilometers per hour, we'll want to deal with that. The question is, determine the total mechanical energy at B. So total mechanical energy is the gravitational and kinetic energy added up. So that's not too difficult. One thing that we'll want to do, I want to get rid of that right away here. So I'm going to do 11.2 divided by 3.6 to give me 3.11111, a whole bunch of ones, meters per second. Meters per second is much better, and it's constant speed, so 3.11111 meters per second at the bottom as well. Cool, so let's go through and let's start plugging stuff in. My mechanical energy, well, that's just my kinetic energy plus my gravitational potential energy, EPG. There we go. Made a bit of a mess, but we got it back. So my kinetic energy is 0.5 mv squared, and my gravitational potential energy is mgh. H. There's just one little piece that we got to look at this before we actually put numbers in. Kinetic energy, no problem. That's a piece of cake. It's always positive. But this height, if I've got a height of 0 here, that means I've got a height of less than 0 here. So I might call that negative 0.8 meters, and I automatically change the centimeters into meters. Or in other words, I've got less than 0 gravitational potential energy at that height. So again, you could think about this in one of two ways. You could call the height negative because it's less than 0, or you could just say the whole thing, the whole gravitational potential energy is negative because it's still less than 0. So from here, I think you could probably plug some numbers in and solve. So put the video on pause and plug numbers in real quick and solve, and I will do the same. Alrighty, so I plugged my numbers in. Again, a really important thing is that this is less than 0 for our height, which means we're going to have less than 0 mechanical energy, more like on a number scale kind of thing. So my mechanical energy, when all is said and done, worked out to be negative 0.75 joules. Again, that is not a direction. That's just saying that we have less than 0 mechanical energy, which is kind of weird, but works out. Anyways, that is our lesson for today. A nice short one. Make sure you're doing the practice, make sure you're understanding, and make sure you're asking questions if you're not understanding. Anyways, that's it for now. Have a good one. Physics 20s. We'll talk to you again soon. Bye.